All right, welcome back. This is going to be our last video for the cells unit, and it's going to be all about water potential, right? Water potential. Everything for the cell unit has been building up to this important concept. And so this is all about what is water potential. And we're going to work on this quite a bit in our asynchronous session, working on some practice problems. So don't worry if you don't understand everything from right now. Also, I would suggest going under the tasks for today and opening up the AP Biology formula sheet and saving it on your computer because you're going to need this for the rest of this class. You're going to need the AP Biology formula sheet because it's going to be super important to use for the test, and it's actually going to be given to you on in the test booklet when you take the AP Bio test. So, water potential is the force responsible for the movement of water in a system through diffusion. So, the force that is causing water to move from one area to the other. We use the Greek letter psi to represent water potential because water potential is going to be a quantitative measure, it's going to be a number, and it's measured in units of pressures, so bars or megapascals. And you'll see on your formula sheet when we're in our asynchronous session all about that. So, conceptually, and these are just words that I use to help you conceptually think of what this number means, it's a quantitative number that measures how much water wants to move via osmosis from one place to another. So if we were going to assign a number, like say 10 was I really want to move from here to there, and 0 is like I'm cool chilling out here. How bad does water want to move bad in quotations from one place to the other? So we're going to figure that out, being able to compare two situations via a number and say in which case does water want to travel from here to there more, or in which direction is water going to move if it's not as clear cut as some of the examples we might have done before. So there is two components, and if you're looking at your AP Biology formula sheet, maybe in a different tab on your computer, you can see it has what is called the solute potential, also called the osmotic potential, and the symbol for that is that same psi sub s. That's what we call it, psi sub s, which is determined by the solute concentration. So that's how much stuff is dissolved in the water. So the more things that are dissolved in the water will have a more negative solute potential. And then the other part is called the pressure potential, or psi sub p, that's what we call it, which results from like pressure being exerted on the membrane or the walls as water moves in and out. So think about it as you're filling up a balloon with air, the balloon starts to push back on the air you're putting in there and that creates pressure. That's kind of like the pressure potential. All right. Or if you're blowing up a balloon and your friend comes by and squeezes it in your face, that's another good analogy for the pressure potential, psi sub p. Both of these things together, so both of them together make up the psi sub w, or your water potential, that number that tells you where water is going to want to go. So a key thing you need to remember is the water potential of pure water with nothing dissolved in it in a glass or an open beaker. That means it's just open to the environment and that's it, is 0. Because pure water has the highest concentration of water molecules as possible. There's nothing else in there. So the water potential of all other solutions are lower than water, lower than 0 or negative. Okay? Unless you're exerting some sort of negative pressure, everything else will have a water potential that is negative compared to water. So here, pure water in a glass, open beaker, water potential is 0. Adding solutes decreases the water potential. The more solute or stuff you dissolve in the water, the more negative the water potential becomes. So solute potential will be a negative number if you're not dealing with pure water. So solute potential will always be negative. If we do some calculations, or you do some in your homework, and you come up with a water potential, or not a water potential, but a solute potential, psi sub s, that's positive, you did something wrong, go back and check again. All right, so water potential is equal to our solute potential plus our pressure potential. So pretty easy equation. We just add two things together and then you get your water potential. The idea is that our water potential can tell us how badly water wants to move via osmosis from one area to the other because water will always move from areas of higher or less negative water potential to areas of lower or more negative water potential. Water always moves from areas of higher or less negative water potential to areas of lower or more negative water potential. Water always falls from high to low water potential. This will occur, that movement will occur until the water potential inside a cell is equal to the water potential outside of the cell. Okay, so your old ninth grade biology teachers lied to you. Osmosis does not continue until the concentrations of solute are equal. No, that actually probably will never happen. Diffusion or osmosis of water will continue until the water potentials are equal between the two substances. So if this makes no sense to you at all, whatever, this is the key. Water potential is equal to solute potential plus pressure potential. The water potential of pure water is zero. Water moves from areas of higher water potential, meaning less negative, to areas of lower water potential, meaning more negative. This is the key information. This is the stuff you have to know. All right, so stop on here, pause on here for a second just to make sure. So let's try a problem. A solution in a beaker has sucrose dissolved in water with a solute potential of negative 0.7 megapascals. A flaccid cell is placed in that beaker then that flaccid cell has a solute potential of negative zero point 0.3 bars. What is the pressure potential of the flaccid cell before it was placed in the beaker? Give you a minute to think about it. All right. Well, if it's a flaccid cell, that means it's loose. It's not full up with water. So the cell wall isn't pressing back on the plasma membrane. So there's no pressure. Pressure potential would be zero. So what is the water potential of the cell before it was placed in the beaker? If we just said in part A that the solute potential is negative 0.3 and the pressure potential is zero, and we know water potential is solute potential plus pressure potential, negative 0.3 plus 0 is negative 0.3, and that is what the water potential is. What is the water potential in the beaker containing the sucrose solution? Well, its solute potential is negative 0.7 megapascal. It's just in a beaker open to the environment, so there's no pressure potential either. So its water potential is negative 0.7. How will the water move? So let's look back here. First, I need to correct an error in this, and that would be that I have two different units, idiot. The solute potential of the solution was megapascals and the cell was bars, so I'm going to say, let's keep the units the same, megapascals. All right. Which way is water going to move? Remember, it moves from less negative to more negative. The cell has a less negative water potential. The solution has a more negative water potential. So it will move from the cell into the solution. Now, is the cell hypotonic or hypertonic with respect to the solution? Well, if the cell has a lower water potential, it's going to be hypotonic because things move from hypotonic into hypertonic solutions. So the cell is hypotonic and the outside solution is hypertonic. So if it is, and we just said hypotonic, this means that its water potential is higher, closer to zero, because there's less solute. And solute makes the water potential more negative. Aha, starting to make sense. All right. If you're totally lost with this, we're going over this in the synchronous session too. So just maybe look at this and save some questions for me when we go through some problems together. So let's try this. A solution in a beaker has a sucrose dissolved in water with a solute potential of negative 0.5 bars. A flaccid cell is placed in the above beaker that has a solute potential of negative 0.9 bars. What's the pressure potential of the flaccid cell before it's placed in the beaker? It's just a flaccid cell. No pressure is being exerted by it, the cell wall or membrane, so 0. So what is the water potential? Remember, the water potential equals the pressure potential plus the solute potential. So that equals 0 plus negative 0.9 equals negative 0.9 bars. What is the water potential in the beaker containing the sucrose solution? So it's just a beaker, open to the environment. No pressure being exerted on it, so the pressure potential is 0. So again, we've got the water potential equals the pressure potential plus the solute potential, or equals 0 plus negative 0.5 equals negative 0.5 bars. Perfect. How will the water move? From less negative to more negative. Both of these are negative. From the solution into the cell. So from solution into the cell. What is the pressure potential of the plant cell when it is in equilibrium with the sucrose solution outside? Also, what is its final water potential when it's in an equilibrium? Let's go back. So, if we say that now water is traveling from here into the cell, all right, these two water potentials need to be equal. Need to be equal when all is said and done. So water is going to travel in here and out of the sucrose solution. So at the end, they will both need to be at the same water potential. So the final pressure potential of the plant cell is equal to zero point 0.4 bars. Or wait, give me a second. Of, yes, will be zero point 0.4, right? Bars. Because negative zero point 0.9 plus zero point 0.4 equals negative zero point 0.5, which is equal to the water potential of the beaker of sucrose solution. Is the cell now turgid or flaccid? Well, if water was going into the cell and increasing the pressure, it's now going to be turgid. It's now going to be stiff because it's full of water. This is all I want to do for right now. There's going to be more to this, but I think I want to go over that in the synchronous session together. I don't want to do anything more asynchronous because otherwise I think you'll get way too confused. So this is going to be it for right now.